This is the computer organization and architecture class. And in previous chapters, we were preparing for this major chapter, chapter 4, the processor. We know that the CPU performance have three factors: the instruction count, which determined by the ISA and the compiler, the CPI, determined by the CPU hardware, and the cycle time, determined by the CPU hardware as well. In this chapter, we will examine two MIPS implementation. We will start with a simplified version, and then we will end up with a more realistic pipeline version that has a big advantage in terms of performance. We are adopting a simple subset of the MIPS ISA. We only focus on the following instructions for memory reference: the load word and store word; for the arithmetic and the logical instructions, add, sub, and, or, and set less than; and for the control transfer, branch equal, and jump. So from all the MIPS instructions, these are the ones that will be implemented in the simplified version of our processor and also for the pipeline version. Now, a quick look at what the processor should do. Mainly, it should do the instruction execution by starting at the beginning in the program counter, and then the program counter have the address of the instruction that we should execute at the moment. So we go to the instruction memory, and notice that now the memory, we are splitting that into two. One of them is the instruction memory, and the other one is the data memory. So right now we are in the instruction memory, and the instruction is there. The PC help us identify which instruction that is the current instruction by having the address. So we do the fetch, meaning that we are fetching the instruction outside the memory, the instruction memory, and then we start decoding the instruction, which means that you are splitting the fields of the instruction. You get the opcode, the specific registers, if you have an offset, if you have an immediate value, things like this. So you decode the instruction. After that, one of the important piece of information in the instructions, most of the instructions actually, are the register numbers, which identify which register you want to read from the register file, and you get it out from the register file, you supply it to the ALU for the execution. So up to this point, we did the fetch, decode, we read the registers, and now we are executing the instruction in the ALU. Now, it depends on the instruction itself. Some of the instructions use the ALU to calculate the arithmetic result, and those most of the R-type instructions, like the add, subtract, the and, the or, and so on, they just execute. They got the two. They read the ALU, get the two read registers from the register file, do the jump of the operation of the instruction, and supply us with the output at the output of the ALU. Now at this point, for the arithmetic operations or the arithmetic instructions, we could write back the result into the register file. So there is a possible write back to registers at this point. We have also some other instructions. They do a memory access. So what we do for the ALU, we have the base register, and we add to the base register the offset or the displacement to get the correct address of the data memory to do the load or the store instruction. So for the memory instructions, you do the base plus the displacement or the offset. Here you do the arithmetic instructions. We also could use the ALU to calculate the branch target address or compare registers. Now, if the instruction access the memory, meaning it's a load or store, we go to the memory, and then if it is a load, we get the address. It tells us exactly where is the piece of data inside the data memory, and we get it outside the data memory, meaning right now for the load operation, we are reading from the data memory, and there is for a load, you need to write back to the register files in the destination register. If it is a store, then you give the data memory the address calculated by the ALU, and also the data that you want to store, and you give it to the data memory, and you save inside the data memory, and you don't need to write back anything. For the store, there is no write back. This is basically a quick overview of what the processor should do. Now, in this chapter, we will build the CPU piece by piece until we reach to the final design of the processor. So this is an overview of what we just talked about, but it's drawn close to the way we will end up in the processor design. So we have the program counter. You go to the instruction memory for the fetch. You'll get the instruction here, and you can see that there are pieces of the instruction going everywhere because we are decoding the instruction at this point. We have the register numbers for the registers that we want to read, and also the register number of the register that we want to write, meaning the destination register. And for the register number that ought to be read, they will be read in those outputs, supplying the ALU for execution. You get the result, and there is a possible write back if it's an arithmetic instruction. If it is load or store, then this is the base plus the offset. You go and access the data memory. It depends on the instruction itself. Is it a load or a store? If it's a store, then you have the address and the data going inside the data memory. If it is a load, then you give the address, and you expect the content of this address to be read outside the data memory and its output, and there will be a write back in the register file. The only piece that we didn't talk about yet is how to get the next instruction. So you know the execution in any assembly code, you go to the first instruction. Once you're done, you go to the next instruction, and then the next instruction. This is a sequential execution of instructions. And for the sequential execution of the instructions, you need the program counter to be updated by the value of the next instruction by having the target address or BC plus 4, and this will point to the next instruction. The reason we're adding the 4, we've talked about this in the previous videos, and this is basically because the instruction width is 32-bit, and 32-bit is actually 4 bytes. So if you are pointing to the current instruction right here, the next one is going to be this place, which is this current address, plus 32-bit or 4-byte. So it's BC plus 4. And to do this in a hardware way, you take the program counter and you add 4 to it. And this way you get the next instruction. Now, this adder, in case your instruction is a branch. So if the instruction is a branch, you get the BC plus 4. You get the BC plus 4, and you supply it with the offset or the immediate value from the instruction, and you add the BC plus 4 plus the immediate value to get the target address where you should store it in the program counter, meaning you have the label inside the program counter to point to the location that you want to jump or branch to. So as you can see for this CPU quick overview, we have those places. We cannot just join wires together. We just join this wire and this wire together in one wire. Similarly, this one. Similarly, this one. In digital design, if you have two choices of wires and you should pick one of them, we should use multiplexers. And this is what we are going to do in the next slide. You can see that whenever we have those lines, we are adding a multiplexer. We added a multiplexer here, we added a multiplexer here, and a multiplexer here. So this multiplexer, it tells you that the second operand that goes to the ALU, it's either going to be an operand coming from the register file, or it's going to be the immediate value coming from the instruction itself. This multiplexer tells you, let's go back to this one. This multiplexer must have a control to choose between those two lines. There will be a control unit. This control unit will be supplied by the opcode of the instruction. And based on the opcode of the instructions, it tells the control lines what to do. For this specific multiplexer, it tells the hardware which line should you choose, this line or this line. Is it going to be a register from the register file, or is it going to be an immediate value that you need to supply to the LU to work on? So if it is an arithmetic or instruction, you need the second operand as a register. If it is a load or store, for example, then you need the immediate value, meaning that this is the displacement or the offset, and you add it to the base register. Now, for this multiplexer, it tells you if you want to write back to the registers, where do you write back from? Do you write back from the output of the ALU, or you write back from the output of the data memory? Writing from the data memory, this happens if you having a load instruction. So you had the data already in the output of the data memory, and you want to write it back inside the register. For all arithmetic operations that has 3 operands, 2 of them will be the source, and 1 of them is going to be the destination. The destination should be written back to the register file. For this multiplexer, it tells you, should you get a BC plus 4, which is the next instruction, or should you get the target address of the branch? And the target address is going to be BC plus 4 added with the label that comes from the branch instruction. So you can see that the control line here is there going to be a branch or not? If there is a branch and the the comparison between the two registers that you are comparing with give you its result, and it's satisfiable that you need to branch, then this will choose this line. This multiplexer will choose this line and load its content in the program counter to jump to the right instruction. Now, in this quick processor architecture, there are some pieces that are missing. For example, what are exactly the control lines? Even though some of them, we written them somehow, like this one. This is a control, tells you that should you register right or not. So is a write allowed to the register file or not? If it is 1, then you can write into the register file. If 0, then you can't. Similarly for the memory read and the memory write. But there are others, for example, the control that's supplying the multiplexer, they are not quite complete yet. Also, how do you decode the instruction? Which piece of the field goes here, or which piece of the instruction, what field goes here, what field goes here, and so on. Also, there are other things that will be complete while we are building this hardware step by step. So we will do this in the next few slides. We will build the data path. A data path, they are the elements that process data and addresses in the CPU, meaning the movement of the data in the hardware. It will move from the program counter to the instruction memory, through that going to registers, going to ALU, through the muxes, different memories, and so on. And if you go back here, they are the black lines that you see in this hardware or in the processor design. Any black line here is a data path. The blue lines here, they are the control paths. The control paths. This is for the data path, and we will also build a MIPS data path incrementally, refining the overview design. And once we are done with the simplified version of the processor, we will go after that to the a more advanced pipeline version that takes into consideration a better performance. So that's one of the beginning pieces of the hardware. We have a program counter. We know that the program counter should be 32-bit register. So this is going to be the read address of the instruction memory, and it will give you the instruction as an output of the instruction memory. Now for this adder, you'll increment it by 4 to get the next instruction. Now, for the register file, now as you can see, we have more details. We have read register number 1, which is the first operand. You know that any R format instruction read 2 registers operands and then perform the arithmetic or the logical operation. And after that, you write back the result into the right register. So we have 2 read register number 1, read register number 2, and these are going to be 5 bits because we know that the number of registers here are 32 registers, and to distinguish between each one of them, you need 5 bits. So you have 5 bits for read register number 1, 5 bits for read register number 2, and this will give you the data. So this is basically like an address that tells you where is the register, and then you get the data from the correct register into read data 1 and also into read data 2. So once you know the address of read register 1, you get the data in read data 1. Once you know the address of the read register number 2, you get its data into read data 2. And now these data are ready for the ALU. You supply it to the ALU. The ALU will do the job, and we already describe how to build the ALU from scratch. And we did that at the beginning, before we, as a revision, before we started with the chapters of our textbook. I suggest that you go back and check how did we design the ALU in detail. Now, because the ALU do certain operations, we have an ALU operation selectors here, 4 bits, so tells you exactly which operation you are going to do with these 2 operands, and you will get the ALU results here. Now, this ALU result need to be written back to the register file. So you give the data here. So it's like you will go back here. This is why we call it write back. And then you will give the control of register write, and make sure that it is 1. And then you will take the register write number or address from the instruction itself, which is the destination, the RD. You get it from the instruction, and this way you know exactly where do you write this data inside the register file. So notice that these 2 goes together. This is the address, this is the data. These 2 goes together. This is the address and this is the data. This is for reading. You give the addresses here and you got the data here. And those 2 for writing back. You need the address, and also you need the data that you want to write inside the register file. Now, for load and store instruction, you need to deal with the data memory. So you read the register operands. There is a register, the source register for the base, and you need to add to it the displacement or the offset. So you have the base register, you add to that the offset, and this is the job of the ALU. And once you are ready, the ALU give you the result, the addition result, and you can give it to the address. Now, if you are loading, or you are using the instruction load word, this means that you want to read the memory and update a register in the register file. So you read the data from here and you write it back into the register file for the load. So for the load, you use those 2. Also, since you are reading, you need the memory read to be 1. Now, for the store, you write the register value to the memory. So you need the data that you want to write inside the data memory, and you also need its address. And the address calculation is similar to the load. You have a base register, usually this is RS, plus the offset or the immediate value that you see here. So you need the base plus the offset, or the base plus the address, and you give it to the address. You know that the ALU, going back to the previous slide, the ALU expect 32-bit here and 32-bit here. This 32-bit, for sure, it will be a register coming from one of the registers. Now, this 32-bit, if this is load or store, it will be an immediate value, or what we call an address here. Now, this address is 16-bit from 0 to 15. It's from 0 to 15. So what we do here is we need to get the address or the offset or the immediate value from the instruction, which is going to be 16-bit, and we do a sign extension. We need a sign extension to make it 32-bit, so the ALU can take it and do its calculation and supply the memory, the data memory, with the address. And to do this, we need the sign extend logic. So it takes 16-bit and it generates for you 32-bit. And it do the sign extension, meaning that for the 16-bit, it looks at the most significant bit, and this would be the sign. If it is 0, it repeats 0 in the left of the address or the immediate value to convert it from 16-bit to 32-bit. If it is 1, it replicates once to convert it from 16 to 32 bits. Now, we just need also to talk about the branch instruction. You read register operands in the branch, and you compare the operands. To compare the operands, what you usually do, you subtract. So you use the ALU to subtract and check the result. If the result is 0, this means that those operands are equal. Now, you calculate the target address. That's the first job of the branch. It compares the operand by using the ALU, meaning you subtract and then check if the result is 0. The other job of the branch is to calculate the target address. To calculate the target address, you need the displacement, which is the immediate value of the branch instruction. It also has 16 bits. And then you shift it left 2 places to get to make it multiplied by 4. So now the offset is ready, and you add BC plus 4 to the sign extended displacement shifted by 2. You add to that BC plus 4. Now, to do the branch instruction, this is what we have. You get the immediate value from the instruction. You sign extend it to make it 32 because this adder needs 32-bit here. So you do the sign extension. And we do the sign extension here because sometimes we branch forward and sometimes we branch backward. Now, it's ready here. In the at this point, you have the immediate value, sign extended, and after that, you shift it left by 2. So it's already multiplied by 4 here. When you shift left by 2, you are actually multiplying by 4. And then you add to that BC plus 4. Now this BC plus 4, you already have done it because you have the BC, you have an adder to generate the BC plus 4 in case you want to go to the next instruction. So now you have the BC plus 4, you supply it all also to the other adder to calculate the branch target. Also, you need the register write. More importantly, you need to use the ALU because the ALU will compare the 2 registers of the branch instruction, and if they are equal, it will make this 0 detection line equal to 1, meaning that they are equal. And this should go to the branch control logic to choose between the options. Now, as you can see, we mentioned here that we shift left by 2. To shift left by 2, you just reroute the wires. To reroute the wires, if we say that this adder is actually this one, so we have BC plus 4, and we have the line coming from the sign extent, We will call it A. It's from 0 to 31. And you need to do shift by left by 2, and you supply here at the output of the shift left 2 the variable B from 0 to 31. Now, how to do the rerouting or rewiring? You do it by what you've seen here. You have the A from A0 to A31. For the B, you just put zeros in place of P0 and P1. So you supply 0, or you connect it to ground, to B0 and also to B1. And A0 goes to B2, A1 go to B3, A2 go to B4, and so on. You continue until you reach to A29. Notice that A27 will go to B29, A28 will go to B30, A29 will go to B31, and A30 and A31 will be dropped. We are not gonna use them. In this way, we just shift it left by 2. So you can see that shifting lifts in hardware is very easy. You just reroute the wires. Now, at this point, we can compose elements for the R type, for the load, and for the store, and we make the data path for all of them. So this is the first cut data path, which does an instruction in 1 clock cycle. Each data path element can only do 1 function at a time, meaning all of this hardware will do, for example, a load, or all of it will do a store, or all of it will do an R-type instruction, let's say add or AND. So once you have an instruction, it will hold all the hardware. Hence, and because of this, we need separate instruction and data memory, because you need to have the instruction and at the same time you need to access the data memory. And this is the reason we split the instruction memory and the data memory. And we use multiplexer where alternate data sources are used for different instructions. So as you can see, now here we have the register that we just discussed. We have also the ALU. And now the MUX, we know its control line. The control line is called ALU source. So this ALU source, it could be from the second operand of the register file, or its sign extended from the instruction, meaning the immediate value. If you have an arithmetic R-type instructions, you will use the second operand of the register file, or you will make this one activated or chosen by having the ALU source equal to 0. So if it is 0, you will choose this. This is for the R-type. Now, if you have a load or a store, you should choose the sign extended value. So you should make the ALU source equal to 1. And the reason, in load and store, we need to use the ALU to calculate the address of the data memory by having the base register plus the offset. You will get the offset or the address or the displacement or the immediate value. You'll get it from the instruction. You sign extend it, and then you give it to the ALU. And this way, the displacement is ready. And you need to add to it the base register. And the base register, you get it from the register file. Also, if your instruction is a branch, at this point, if we are using this ALU, then we need to use also the sign extended value. However, what we've done before, we didn't do this. We didn't use the ALU. We use the sign extension, and we have our own adder to calculate the branch target. And since we are doing this, we don't use the sign extended. We don't use this multiplexer for branch. So this will be if your or the ALU source, if it's equal to 0, then this means that the instruction is an R type. Now, if the instruction load or store, you should make this equal to 1, indicating that you need the offset and you need to add the base register to the immediate value to generate the address that goes to the data. For this multiplexer, we have the control called mem to reg or memory to register. So the purpose of this multiplexer, and notice that it's flipped. This mux is 0 and 1, while this mux is 1 and then 0. It's flipped. Be aware of this. So if you want to write back to the register and you want the output of the ALU, meaning that you have an R-type instruction running now, so you need to write back and skip the data memory completely and go to the register file, because the R type doesn't access the data memory. So at this point, you have to make this equal to 0. If your instruction is load, then the load will have the memory to register equal to 1, which means that you get the data read from the data memory and you write it back to the register file. Now notice in store, if your instruction is a store, you don't write anything back. In store, actually, you having an address and you also have the data coming from the second operand here, and you store it inside the data memory. Now, we completed the full data path by adding this piece that you see in the top. You can see that in the shift left by 2, you took the signed extended value, meaning if your instruction is a branch, you don't use this ALU, you go shift left by rerouting or rewiring, and then you add BC plus 4 to this immediate value that is shifted left by 2, and then you choose it to be in the BC and be written in the BC if your BC source control equal to 1. The BC source should be equal to 1 if the instruction is a branch instruction. That's the first condition. The second condition, there should be a 0 coming out here, indicating that those two instructions are equal. So the condition is satisfied. So if this is also true, then the BC source should be equal to 1, and you should choose BC plus 4 plus the branch label that is in the instruction itself. You do the sign extension followed by shift to the left, and then you add it to the BC plus 4 to go to the to generate the target address at the end. Otherwise, if there is no branch, then you should run the code sequentially. And this means the BC source should be equal to 0. So the BC will be supplied by BC plus 4, indicating that you should go to the next instruction. Now, we've talked about the ALU source. We've talked about the memory to register multiplexer and this BC source register, the BC source control. We have also the register write, the memory read, and the memory write, and we've talked about them. We have those 4 bits that tells the ALU what job should it do. Those ALU operations are listed here. So in the ALU control, those 4 bits, if they are zeros, then you are doing an AND. If they are 1, 0, 0, 0, then you are doing an OR. Your instruction is an OR instruction. If it is 0, 1, 0, 0, then you are doing an add instruction. If it is 0, 1, 1, 0, then you are doing a subtract. If it is 1, 1, 1, 0, then this is sit on less than. If it is 0011, then this is an OR instruction. The NOR sometimes are used also for negation. And we've described this in the revision at the beginning of this course. And just to remind you, for the add, for example, we choose that 01 is the multiplexer input, where you choose 01 here, 00 and 10. 01 is the addition or subtraction for that matter. The 00, it tells you that the operand A that you are going to add, because you are adding two operands, A and B. The operand A is in its normal form, and also the operand B is in its normal form. It's not complemented. So the A is not complemented and the B is not complemented. This is what we mean by this. You notice that for the subtract, we use an adder, but at this point, B is complemented. Because what we are doing here is we are taking the 2's complement of B. So if you are subtracting A minus B, what you should do is you should convert this to addition, and you take the 2's complement of B. And the 2's complement of B, this minus B, the 2's complement of B, is actually equivalent to B bar, or the first complement of B. You complement everything, and this is why we're having B complemented, plus 1 in the carry-in. And we've described this in the details previously in the beginning of the class. Now, the ALU used for load and store function, you should add, because you are adding the base register to the offset. In the branch, you should subtract, because in the branch, you use this ALU for this line to compare between the two registers. Now, just to remind you, this hardware in the branch, it calculates the target address. But the branch also uses the ALU to compare between registers. So it needs this register and also this register. Now, the R type, it depends on the function field of the R type itself. And to see the different function fields and what is the capability of the ALU, this is a detail view. This is the table that we just discussed. We assume a 2-bit ALU operation derived from the opcode. So you get the opcode, it has 6 bits, and you get 2 bits. Those 2 bits will be op0 and op1. This is from ALU opcode. So this is ALU op0 and this is ALU op1. If it is 00, it will be 00 for load and store. And it will be 10 for the branch and 01 for the R. Since we are focusing only on those 4 instructions or 4 type of instructions, we stop at this point. If there is another type, probably we'll give it 1 and 1, but there is none right now. So we assume 2 bits of ALU op, as we've said, and this is the corresponding truth table. It will be 00 if it is load or store. If your instruction is load or store, irrespective of the function field, because actually you don't have this in the instruction itself. You have an immediate value spanning from 0 to 15. So you don't care about the function field if it is load and store. And for that matter, also if it is branch, because the branch is an I-type instruction. So all the I-type instruction, load, store, and branch equal, they don't care about the function fields. The load and store, they need the ALU for addition to add the base to the offset, the base register to the offset. and the branch, you need to subtract. You need to use the ALU for subtraction to check the equality of the two registers. So you subtract. If they are 0, this means the two registers are equal. Now for the add, we know that the add is 0, 1, 0, 0. And this is why we give the ALU control, the 4 bits, ALU control 0, 1, 0, 0. We know the subtract is 0, 1, 1, 0, and this is what we give here. Now for the R type, we should have the ALU up 0, 1, and we get this from the opcode that is in the instruction itself. And it depends on what is the R type instruction itself. If it is an add, then the function field will be this way, and we got this from the table. If you remember the table when we talked about the ISA in the chapter that we discussed the instructions, there was a table that tells you the opcodes. If it's an R type, you need to go a little table below that tells you the function fields. And the function fields for the add is 0, 0, 0, 0, 0, 1. We got it from that table. For the subtract, it's 0, 1, 0, 0, 0, 1. And you notice that there is only one difference in F1. For the AND, is 0, 0, 1, 0, 0, 1. For the OR, 1, 0, 1, 0, 0, 1. Also between the AND OR, there is a difference only in F0. And for set on this, than, and we know that this this instruction, set less than, is important when you are doing a branch that have less than or less than and equal, larger than or larger than or equal. We use this before the branch. So this is the function. This is the function field for it. 0, 1, 0, 1, 0, 1. Now, for the add, obviously you will do an add, and this is the code for it. This is the add. Subtract is 0, 1, 1, 0 from here. For the AND, we get the AND. For the OR, we get the OR. You can see that we copy it here. For the set on less than, you get the set less than that you see here. 1, 1, 1, 0. Now, just to remind you about the different type of instruction, we have the R type, and here we are focusing only in these: add, subtract, and OR, and set less than. So the R type will have 0 in the opcode, and it depends on the function field, which is bit from 0 to 5. Now, we have the RS, RT, and RD. Remember that the RS from 21 to 25, and the RT from 16 to 20. This will be mapped to certain boards in the hardware, and I'll show it in the next slide. The RD is from 11 to 15. Now, in the shift amount, since we are not going to discuss a lot about the shifting, we're not going to use it much. When we use it, sometimes to indicate the index of an array, we will show it at the time. For the load and store, we have 35 or 43. 35 in the opcode means that this is a load. 43 is the store. And this is the opcodes for the load and the stores generated from or copied from the table, the big table of the ISA, or the MIPS ISA. The source register and the RS and RT, they are indicated by those bits, similar to the R type. Also for the branch, they are the same. The branch opcode is 4. So remember that the branch is 4. And we have the addresses. Now this address is the displacement or the offset for the load and the store. And this address for the branch is actually the label that you want to branch to. It's important to know that these are the opcode. Now the RS is always a source register, meaning that we always read it. It will be read from the register file. For the RT, we always read it except for load. So if it is an R type, we read it. It's a source register. If it is a store, the store gives you the data and the address as well. So for the RT, sometimes it's a source register, sometimes it's destination. If it is R type or the store, then it's a source register. Also for a branch as well, it's a source register. The reason is the R type, the destination, we know that it's RD, so this definitely is going to be a source. For the store, you need the RS to be the base register, and you add to this the address to generate the address. To generate the address that goes to the data memory. This will be the base register, and this would be the offset. For the RT, it will hold the data that you want to store or save or write to the data memory. So this is a source, it's not a destination. For the branch, this is going to be the second operand that you are comparing. So you compare the RS against the RT and check if they are equal or not. The only instruction that the RT is going to be destination is the load instruction. So what happens is you take the RS as a base register, you add the offset to the base register to generate the address that goes to the data memory, and you read the data memory. It will give you the data in the output of the data memory, and you write it back to the destination RT. So this is a destination register for the load. For these two registers, this is actually always a destination. So you write for the R type, you write back to RD. For the load, you write back to the RT. You know that these offsets or these addresses from 0 to 15, those 16 bits, they are signed, extended, and they are also added after the sign extension. So see all of this, all of these we discussed so far in one data path. This is the data path. Now it's kind of complete. And as you can see here, the instruction, we know exactly which fields goes to which piece of hardware. So you know that the control needs the opcode, and the opcode is from 26 to 31. That's the 6 bits that goes to the control. Also, we mentioned the ALU op. We have 2 bits, only 2 bits, which is the ALU op 0 and ALU op 1. Those 2 bits goes to another smaller control, which is the ALU control, to tells you which operation that you should do. So based on the ALU op, also based on the function field, which is the instruction from 0 to 5, it tells you exactly what the ALU should do, following the table that we just discussed here, this table. So it has the 2 ops coming from the control. First, the control get the opcode, the 6 bits. It get the 6 bits, and from that it gets only 2, or it gives this control, it gives to you as an output 2 bits, and those 2 bits are the ALU op 0 and the ALU op 1. And based on those 2, and also the function field, because in the R type you need also the function field, the distinction between the different functionality of the R type. Based on those information, it tells you exactly what are the 4 bits that you need to supply to the ALU. And this is what happens in the ALU here. We have 4 bits goes here. And here we have only 2 bits. Now, the data path, we already discussed it. We already discussed what the register do, the sign extension, the ALU, the data memory, this piece here, the adder and the other adder, one of them BC+4 and the other one to calculate the target of the branch. Just check the control again. You see the register write goes here in case you want to write back to the register. You know that the ALU source goes to this multiplexer to choose between the register or the sign extended value. This goes to memory write. This goes to memory read. You have also memory to register that goes to this mux. Should you write back the result from the ALU or write the result from the data memory back to the register? You have also the branch. If the instruction is branch and at the same time the comparison gives you 0, which means that they are equal, at that point you should make the BC source equal to 1, and this is why we use an AND gate going to this multiplexer to get the BC plus 4 and then get also the immediate value going from the instruction, which is from 0 to 15. We sign extended to 32 and then shift it left by rewiring and get the target address back to the program counter. You can also see, if you focus on the register file, that the first register read is the instruction from 21 to 25. Going back 21 to 25, this is the RS. So we know that this is RS. The second register, read register 2, this is RT. From 16 to 20. 16 to 20. So this is RT. And here you get the data coming from the register RS. You go check where is the RS. Maybe it's register number 8, 16, whatever is the register number. You have 32 register from register 0 to 31. And also register 0 is always 0, so you cannot use it. From 1 to 31. And you get the data here and here. Now, for the register write, sometimes it's the RD, which is from 11 to 15. Sometimes it's the RT. So sometimes it's the RD, sometimes it's the RT. And we said that it's going to be the RD if it is R-type instruction, and it's going to be a destination register if your instruction is load. So the RT is going to be your destination. And this is why we have it this way. So we check this line right there. And to choose which one is the one that is the destination, is it RT or RD, you need a control line, which we call the register destination, that goes from the control based on what kind of instruction you have. So you get the instruction code, and based on that, you generate this control. This is basically the things that I want to emphasize a little bit. And to show all of this that I just discussed, it's rewritten to you in this table. I got all the controls. So you have the signal name, register destination. The register destination will be RT if it is de-asserted, meaning if it is equal to 0. And this is what we have here. If it is 0, then it's RT. If it is 1, then it's going to be RD. Now for the ALU source, the second ALU operand comes from the second register file output, which is read the data 2. So when it is equal to 0, you get the register. And this is what we have. From the 0, you get the register from read data 2. If it is 1, then the second ALU operand is the sign extended lower 16 bit of the instruction, which is what we have here. Now, memory to register, the value fed from the register write data. Input comes from the ALU. So we are talking about mem to register. We are talking about what happens when we write back. So if it is 0, then it comes from the ALU. If it is 1, it comes from the data memory. And this is what we have in this mux. If it is 1, it's from the data memory. If it is 0, it comes from the ALU bypassing the data memory. Or skipping the... I said this before and I'm saying it now. The multiplexers here are all okay, except this one, it's flipped. So be aware of this. Now, the register write, memory read and memory write, these are easy controls. If they are equal to 0, means we don't have register write, we don't have memory read, we don't have memory write. If it is 1, then yes, we do. And register write means that the register on the right register input is written in the register file on the right data input. If the memory read is 1, the memory is allowed. If the memory write is 1, then the write is memory write is allowed. Now, for the branch and the BC source, they are related to each other. And to see it here, you can see that the signal that comes from the control for the branch, it comes from the control, and it needs to be ANDed with 0, meaning that it needs also to check for the registers and make sure that they are equal to generate the BC source. So the BC source is actually tells you that the instruction is branch, and also the registers are equal. And this is what we have here. The branch means that the current instruction is not branch. If it is asserted, if it is deasserted, means it's equal to 0. It means that it's not a branch. When it is asserted, it means that it is a branch. The BC source, if it is equal to 0, then the BC is replaced by the output of BC plus 4. If it is equal to 1, then the BC is replaced by the output of the adder that computes the branch target. So the branch target address is the one that's going to be written to the program counter. So basically, this is what we have here. If it is 1, then you get BC plus 4 plus the sign extended, shifted left by 2, and you got it back to the B program count if the BC source is equal to 1. If it is equal to 0, then you get only the BC plus 4 back to the BC. And at this point, you see the beauty of the things that we discussed in the past. Now we are generating the processor, which is the main and major component of any computer. Now, setting up the control lines. We know that they are determined by the opcode. So this control, it takes the opcode, and based on the opcode, it gives you everything here. So let's try to fill it for our instruction, the one that we took as a subset. And this is what we are going to do here. For if the instruction is R type, it is load, or it is store word or branching. What happens for these controls? So if it is an R format, we need the register destination to be 1. Meaning we need RD to be the destination. And you go check it back here. You see that the R register destination, it should be equal to 1. So we get the RD because it's an R type. For the ALU source, it should be 0. Going back, the ALU source here, it should be 0, meaning that you need the second operand being or coming from the register file, because you need the data of the RS and the data of the RT that goes here, and you supply to the ALU. All of the R-type instructions have to do this. Memory to register. Are you going to get it from the ALU or from the data memory? Since this is our format, you need to get it from the ALU. So you get the ALU, the result, and you feed it back to the register file. And this is what we have here. Memory to register or memory to register. You get the result of the ALU and you write it back right there. For the memory read and memory write, we shouldn't read or write the memory. This is R type, so we don't access the memory. Both of them are 0. Also, it's not a branch, so it's going to be 0. And we need the opcode based on the slides that we have the table on. It should be 0 and 1. All the R format are 0 and 1. I will write it just quickly in the top. 0, 0, this is load and store. Branch of equal. This is 1, 0. And all the R type, the op0 and op1 is going to be 0, 1. So for the load, I'll mention it quickly and you can go and check the hardware. The register destination should be RT. This is why we have 0. The ALU source should be equal to 1 because we need the sign extended value that comes from the instruction. We need the offset, and then we sign extended to 32-bit, and we give it to the multiplexer, and we choose 1 to pass it to the ALU. We choose ALU source equal to 1. Memory to register, for the load, there is a write back. You need to write back from the memory. And because you are writing back from the memory, this should be 1. And since you are writing back, the register write should be 1. Now, this is a memory read. The load is a memory read. So you have memory read equals to 1. The memory write equals to 0. We are not writing. It's also not a branch, and we get 0, 0 for the load. And for that matter, it's also for the store. Now, for the store, there is nothing to write back. And because of this, actually, both of them, the store and the branch equal. There is nothing to write back. And remember this, there is no write back at all for store and also for the branch. And because of this, we don't care about the register destination. We are actually not writing back. And also, we don't care about the memory to register because we are not getting anything back from the memory or even from the ALU. Now, for the ALU source, for the store, you need the ALU source to equal to 1. Just to remind you, this is the ALU source. And you need to make it 1, which is from the instruction, sign extended, and then you pass to ALU. So it's similar to the load. You can see that they are similar here. Now for the register write, for the register write, we make it 0 for the store. Going back, this is the register write, which is this one here. We make it equal to 0 because we don't want to write anything to the registers in the store. In the store, we don't write from anything into the registers. And this is why we have it both 0 for the store and the branch. So basically, for the store and the branch equal, we don't write back. We don't care about the register destination. We also don't care about the memory to register, and the register write should be 0 because we are not writing anything back. Now for the store, there will be a write to the memory. It's not a read, it's writing to the memory. That's what we mean by store. So this should be 1 and this is 0. The branch equal is 0, 0 because there is no access to the memory. It's similar to the R format. Obviously, for the store, it's not a branch, and the ALU op 0 and 1 is 0, 0. For the branch equal, it is a branch, so this is 1. Notice that it's 0 everywhere except if it is a branch is equal to 1. And the opcode 0 and 1 of the ALUs is 1, 0. So this tells you basically the control, this control, check the opcode. If the opcode is for load, meaning it's 35. Convert to this to binary, you'll find in 6 bits from 26 to 31 in the instruction. The hardware knows that this is a load. Directly, it generates all the control for the load, meaning it will generate everything here and give it to the specific other hardwares, which is the muxes, the register, the memory, the data memory, and the different kind of controls. For example, the ALU control. Now, this is an R-type instruction on the RAM. So as you can see here, we are having add. We add T2 with T3, and we get the result to T1. And because the add doesn't use the RT as destination, this is great. Also, it doesn't use immediate value. There is nothing related to sign extension. Notice the part about the branch is also great because this is an R-type. So in the R-type, you need the program counter, you need the instruction memory. Actually, all the instructions need those two. And then you decode the instructions. You notice that you don't need this part because this is tells you that the destination is RT. We care about the RD in the R-type. And you don't use the assign extension. Obviously, you need the register files because you need 2 operands to be read and supplied to the ALU. And then you write back, and notice that we don't have the data memory at all. You write back to the registers in the RD. And you supplied all the controls based on this table that we just see. The R-type, you give these values over here. Also, since this is an add, it's not a branch, the next instruction would be the normal sequential execution of the code. So you need to have BC plus 4 back to the program counter. Now, we didn't use this because this is not a branch. We don't use this because this type of instruction is R-type, it's not I-type. We didn't use the RT because this is not a load. And we don't use the data memory because you don't access the data memory. It's not a store, it's not a load. Let's go to another instruction. If we say that we're having a load, we have an offset and we have a base register. We take this one and then you load the result into register T1. What happens here? We don't use the RD. We don't use the second operand because we need to have the sign extended value as the offset. And this will be the base register. So T2, the content of the register T2 would be here. And the offset would be here. And then you add base in the ALU. And once you finish the ALU, do the addition, you will have the address ready. And then you read the data and you write it back into RT. Notice that RT is a destination, not a source anymore. And because this is not a branch instruction, you don't use this part. It's very important to know now we have a load instruction. So we need all the control lines to be appropriate for the load. So we use the control for the load. This is for the load. And this one for the R-type. So let me number them. This is number 1, and this is number 2. So the control of number 1 goes here when the instruction is add. The controls of number 2 goes here when the instruction is load. To make the right choices for the muxes, the right choices for the register, is there a register right or not? The right control for the memory read and memory write and so on. Now, let's also check the branch. Now, if this is a branch, you need to compare those two registers and then jump to the label. And this is why we have this now valid, because this is a branch instruction. And because this is a branch, the branch, remember, the branch and the store as well, they don't write back. And this is why the write back here and here, all of them are gray. You don't write back here. Also, you don't care about this. There is nothing that to write back in the branch equal. You don't access the memory. This is a branch. The ALU doesn't generate the ALU results. It tells you if they are equal or not, the T1 and T2. This is why we care only about the 0. Notice that the ALU take both registers. Both of them are registers in the ALU. You are comparing T1 registers. So the content of T1 is here, and the content of T2 is here, to see if they are equal or not. You also notice that we don't care about the function field, because this is the I type. Similarly, also for the load, we don't care about this one. We care about it only in the add. So it tells you which one. Is it add, or, and? Is it set plus on then? And so on. Now, finalizing the control. Actually, we just generated these lines for the 4 types that we care about, the R type, load, store, and branch. We just trying to tie this as outputs to the inputs if they are the opcode of the instruction. We just say here that the R format have the opcode 000000. The load is 35. This is 35. The store is 43, and this is 43. And the branch equal is 4, and this is 4. So that's what the control sees. If it sees 0, 0, if it sees 4, 0, 0, 1, 0, 0, 0, it generates those directly in the control lines. And they don't care. It's just a matter of choice. Sometimes it's 0, sometimes it's 1. Both of them are okay. Now, if you remember the set that we considered in our ISA, we've discussed everything except one instruction, which is the jump. And this is why we are checking the jump here. To implement the jump, this is the J type instruction. We only care about the jump. So the jump uses a word address. It updates the BC with concatenation. So we are concatenating the bits. We take the top 4 bit of BC plus 4, which is from 28 to 31 from the BC, and we concatenate it with the 26 bits jump address that is here in the J type from 0 to 25, but they are shifted to the left by 2, meaning that we are rewiring and we are adding 2 more bits. Notice this is 26 bits, and here we have 4. 4 plus 26 is 30. We rewire with 2 bits to do the shift left by 2 to make them 32 to jump to that, or jump to that address. And we need an extra control signal for the jump, and we will call this control jump. And this is what happens in the hardware for the jump. Note that for the jump, we don't use anything here. Everything is gray. If it is a jump, you take the BC plus 4 from here. This will be the BC plus 4. You take only the 4 most significant bits, which is from 28 to 31. And you make those 4 bits here. And then you concatenate it with, you take from the instruction the bits from 0 to 25. You take all of these bits and you rewire them to generate 28 bits. So now you concatenate this for the BC plus 4 from 28 to 31, which is the 4 bits, with 26 and 2 zeros. those 26 and 2 zeros after the rewiring. You'll add those 2 zeros. And this way you generate the jump address from 0 to 31. So notice here that actually we are allowing to have some lines from here and some lines from here, and they are both merging into one line because we are doing concatenation. Otherwise, we would use muxes, as we said. And now we have this control, the new control, which is the jump control. If it's a jump, then you will get the new BC from here. If not, then choose it from here. And it depends. Either it's going to be BC plus 4 or something from the branch instruction generating the target address region. So actually we have this hardware added to the original data path to implement the jump. And here it tells you that each instruction you want to add, each new feature that you want to add to the hardware. Sometimes it doesn't cost anything. You can add a new instruction to the original hardware by doing small changes and adding few lines just to add an instruction or list of instructions. And sometimes you need to add a hardware, as this one. In the jump, we needed some hardware. And some instructions, it changes the hards completely to add. So some instructions have low cost to add to the hardware or to the data path, and sometimes they have very costly tax, let me say. Performance issues. The longest delay determines the clock period, and the longest delay in our data path comes from the load instruction. Notice the load here. We go back to the load. Everything in the load, you are using the program counting, the instruction memory, and you're going back here. You'll use the registers, this mux, and the ALU, and also the data memory, and going back to the mux, going back to the register again. So you use all these hardware. This is the longest delay. For example, if you go to the add, it doesn't use the data memory, so it's skipping the data memory. Other instructions skipping more hardware. The longest one is the load. So our critical path is the load instruction, because you go from the program counter to the instruction memory to the register file to the ALU to the data memory and going back to write to the register file. It's not feasible to vary period for different instruction. Means that you have an instruction cycle for this instruction, another instruction file, another instruction cycle for a different instruction. You should unify the clock cycle time for all the instructions. If you do different cycle time for different instruction, you are violating the design principle, making the common case fast. And that's critical. Now, the disadvantage about this data path is if you have a load, let's say that you have one of the instructions. So let's say you have a branch instruction. The branch instruction will hold all the architecture, even if you are not using it. For example, you are not using the data memory, you hold it. Similarly for the R time. So it would be wise to have an instruction that works in some part of the hardware. Another instruction is making use of another part. So it's wise to share the hardware between different instructions. Now, at this point, up to this point, this is the simplified version of the CPU, where an instruction holds the whole hardware. Now, if you want to share the hardware between different instructions, then you could improve the performance by pipelining. And this is the pipelining idea, and we will discuss this in the next video.